Good afternoon, everyone. So this is the video for circular motion. Um, just a few things before we start with the tutorial. Many of you don't have access to a software, unfortunately. So besides providing with some data that can help you guys complete the lab, as a trial that we're doing for the next semester is using online interactive simulators. So if you don't have access to the exploration of physics, you can always use these online simulators. This is from Physics Classroom. And I want to show you that you can do at least the first part without any problem. All right? Because the lab has 3 parts, and the third part is going to be extra credit. All right, I have decided to make this extra credit. I'm gonna let everybody know via announcements eventually when you get to this lab. But what you will need to do the first part and the second part. The first part is actually not so bad. You're basically just exploring centripetal acceleration, period, speed, and angular speed. The equations are provided in the procedure. So the only thing you have to do for the first part is, if you manage to open this, you are going to leave all these and just make sure that you adjust the accelerations. The centripetal acceleration is v squared divided by r. So this will give me 36 meters per second squared. And that's good enough to have a mass moving at a rate that you can actually use to say to stop the motion there, or to pause the motion. Here you have a graph of how the components of the velocity are changing. So this one is the vector linear speed. But as you know, there are Vx and Vy. So Vy will be positive and Vx will be negative. In the second part, you're going to explore that. They don't give you the values here, but you can see the proportions. So Vy is about 4 times and Vx is about 3 times. So the ratio between Vy and Vx is 4/3, which you can find by looking at the angle here. So if I leave this as it is, you're going to use the time. How? Well, if I play the simulation, you want to find the time for one revolution, which will be that 10.5 seconds. If you have that, that's basically the period. So that will be your value of period. 2 pi divided by period is W. With W, you can find the centripetal force, mw squared times r. M and r are given in here, mass and radius. So there you are. You basically can check your calculated value with the value given here, right? So if I were to do it very quickly, just to show you one try, and you will do this 5 times. So you can change the acceleration, so you get different values, but basically 2 times pi divided by the period, that's my angular velocity. If I square this, multiply by the mass, which is 1, multiply by the radius, which is 100, I get 35.8, close to 36, but it's not exactly 36. So that's good for discrepancy calculations. All right, so you have to do a discrepancy calculation, and that's basically part 1. So in part 1, you're just exploring uniform circular motion. Again, it's not so bad. You just have to make sure that you calibrate the software at an appropriate value. If I were to use, for example, 40, the centripetal acceleration would be 16. So let's see what we get. So that's good. It's going slowly, of course. It's lower than before. Actually, that's 42. Okay. So let's do this again. It should be 40. There. So let's do, yeah. So you can do the calculations again. All right. And then you will have a set of trials. But you can stop it. It might not be exactly what you want, but that's part of the systematic and human error you want to include in this. All right. So part one shouldn't be that difficult. You're basically applying the equations that you have studied in the lecture. Part two, you are going to be exploring the vectors. So if we continue with, or actually, let's give it a bit more. Let's make it 50 here. If I continue with this, let's stop. Also, you want to make this 1. So you can see the real magnitude of the vectors. So if I stop the simulation around here, how to pause it? There. So this is your centripetal force, 25 newtons. And this one is not the angular velocity. Be careful. This is the linear. So this will be 0.50 times the radius. So this will be around 50 meters per second. All right. So this is the linear speed. Remember, right? The circular motion is like this, and the linear speed is tangential. So we also call it a tangential speed. So since I changed the scale to 1, 25 newtons makes sense to be smaller than 50 meters per second, right? Now, you can find the angle here between the force and the horizontal. This angle is 3/4, so it should be 37 degrees. Here. 3 squares, 4 squares. Here will be the same angle as this by alternate interiors. So I'll show you with this. So I trace a line here. So let's use this angle is the same as this angle, which I just said is 37. And I'm sure it's that because I changed the vector scale, right? The scale. So this is the same. Now, the radius of the circle, which is alongside the centripetal force or centripetal acceleration, is perpendicular to any tangent, perpendicular to a tangential speed. So this is 53 degrees. So with that angle, you can find Vx and Vy. And as I said before, Vy will be positive. Why? Because what is, right? And Vx will be negative. So if I use another color, let's use black. So this is your Vx. So your Vy will be like 4K, like proportionally, and Vx will be like 3K. So what I'm trying to say is that Vy over Vx is 4/3. Now, value-wise, if the velocity here is 50, 50 cosine 53 will be 30, and this is like 40. So this is my Vy, my Vx. For one trial only, you're going to do this. So then you can look. This is like 3, this is like 4. Yeah, it works. So you have to show me this, not maybe all this, but the graph, the proportion, and the values you use to estimate this. Not so bad, right? So these are the two mandatory parts. if you were to go to the online simulator, you can, you can play this here. And you can also stop it there. They give you the acceleration and the force, and the value of the speed, the radius, and the mass. So very similar, right? So part one, you should be able to do here. The only thing that you don't have here is time. So I will suggest you guys to use an online timer. Of course. So with the online timer, you can start and then you can check the time it takes for one revolution, right? So you will have to probably open a second window and do this. Or you can use your phone. You can use your phone, make sure that this is not very high speed. So maybe you want to do 15. And then we want to reset this. And then you can easily time this revolution. That will be the period, and then you use the same equations as we show you in exploration physics. What's going to be hard here is to do part two. So if you have trouble opening the software for part two, send me an email so I can provide you with maybe an alternate problem for that part. All right. And if you have the software, then you won't have the issue. Then you can proceed with part three. So part three is the extra credit for this lab. And in part three, you are going to be using, well, if we look at the description for part three, you are going to investigate the centripetal force, the equation. You are going to use at least 4 trials by keeping the velocity constant. You're going to change the value of the mass and radius, and you want to make sure that you adjust the centripetal force. What I mean by that is, let's suppose you want to keep the velocity and the centripetal force constant. So for 60, and for radius of 100, my centripetal force is 36. Then my mass is 1, my radius is 100. Okay. Then you want to change. You want to double the mass, but if you double the mass, you also want to double the radius. But there's a problem though, it doesn't go that far. So you want to start maybe with 40 and with a mass of 2. So you go like this a few times, and then you want to annotate the centripetal force and the velocity. For 180, you get a velocity of 60. Then you want to keep this constant, and then you want to maybe double the mass. If you double the mass, you need to double the radius. And then your centripetal force will still be 180. All right? Can you do it for a mass of 3 kilograms? Well, mv squared divided by r should be 180. So you have to find a radius for that. 180, 360, around, well, that will be a decimal. So you wanna, if you can do it for that, then I will suggest you change the velocity. All right. So maybe this won't be as good. So you may want to do it for, say, 10 meters per second. So we can go to 10. And then let's see what we get for 2 kilograms. 2 kilograms and a radius of 50. 4 newtons. Very slowly. If I make a mass of 4 or 2.5 mass V squared divided by R. So before we got for a mass of 2 was 4 newtons. So if I make it 2.5, if I want 4 newtons, mass V squared 250 divided by 1 radius will give me 4. So we have decimals here. So we may have to change this part a little bit to make the exploration of the centripetal force mass V squared. So let's see. We need to find a value that has several radiuses that you can use. Maybe radiuses of 10. So you can use radius of 10, 20, 30, and 40. And then you want to adjust that with a given mass. And you want centripetal force is mv squared divided by r. So if my radius is 10, I can make my mass 1 kilogram. If my mass is 2, my radius has to be 20. So can we go to that point, 10, 20, 30? Yeah, so that will be the solution, right? Yeah. So if you want to use the same values, that's fine. Just make sure that you show me what you are doing. These are whole multiples of 10, and you can fit them here. They can go up to 140. So yeah, you can start with value of 10 or 20, 40, and 80, or 20. Let's see if you can use 30. You use 20 and then you want to use 30. We need to find a value that gives us a centripetal force that we can use for different masses. So for 1 kilogram, what's the centripetal? So give us 5 newtons. So what you're going to do is you're going to write that this is equal to 5. 5 equals to mass. We're going to adjust the mass. The velocity squared is 100 divided by a radius. So if my mass, so 1 over 20, that's m divided by r. So that's what we have. So we can multiply by 2, or we can multiply by 1.5. So there you are. If m is equal to 1.5 kilograms, then radius will be equal to 30 meters. So there you are. 1.5 kilograms. Yeah, that gives me 5. So you're going to do that 4 times for 4 different values of m and radius. And then you're going to plot. You're going to plot mass versus radius in the x and y plane. You're going to feed a line, and then you're going to find the slope, which is basically the centripetal force divided by the speed square. And then we'll discuss about it. That's why all this part is extra credit, guys. Like if you manage to do that, that's perfect. I would much rather do this remotely, but since you guys are online, you might find this a bit more challenging. If you are interested in doing this part, please send me an email so we can discuss this in a Zoom meeting. I don't mind helping you guys with this. Just make sure you email this or email me on time. As you know, I do office hours on Saturdays, on Wednesdays, May on Mondays. So let's try to do this. But for now, part 1 and part 2 are the mandatory sections. All right. Don't forget to answer the questions at the end of the lab. Other than that, this might be a bit more of a challenging lab. So I'm going to try to give you enough time to complete it. All right. All right. So there it is. I'll be opening another set of discussions for this lab. And then the next lab you're going to be working on after this will be the energy lab. Now for the energy lab, I should be able to activate another simulator for students that have issues using exploration physics. All right. See you in the next video, guys. Have a good day.